Welcome to YouTube channel PGK Kadam Academy. This video is on Grashoff's law.
By understanding this Grashoff's law, engineers can design and analyze various mechanical systems, from simple mechanisms to complex machines, ensuring they operate as intended. Grashoff's law plays a pivotal role in guiding the design and optimization of countless mechanical systems across diverse industries. What is a planar four-bar linkage? Four-link mechanism is the simplest of all closed-loop mechanisms. A four-bar linkage comprises four bar-shaped links that have three moving links, one fixed link, and four pin joints, four turning pairs. S is the crank. A link which can make complete revolution is known as crank. P is the lever or rocker. Any link which does not revolve is called a rocker. Only oscillates, which makes a partial rotation or oscillates, is known as lever or rocker or follower. Q is the frame. The fixed link is known as frame of the mechanism. L is the coupler. The opposite link of frame is known as connecting rod. What is Grashoff's law? Grashoff's law for a planar four-bar linkage or mechanism: when a link can make a complete revolution relative to another link if the sum of the shortest and longest bar lengths is less than equal to the sum of the remaining bar lengths. The sum of the shortest and longest link lengths should not be greater than the sum of the remaining two link lengths if there is to be continuous relative motion between the two links. Mathematically represent as S plus L less than equal to P plus Q. Kinematic chain is a combination of four or more kinematic pairs, such that the relative motion between the links or elements is completely constrained. The simplest and basic kinematic chain is a four-bar chain or quadric cycle chain, as shown in figure. It consists of four links. Each of them forms a turning pair at A, B, C, and D. The four links may be of different lengths. A very important consideration in designing a mechanism is to ensure that the input crank makes a complete revolution relative to the other links. The mechanism in which no link makes a complete revolution will not be useful. In four-bar chain, one of the links, in particular the shortest link, will make a complete revolution relative to the other three links if it satisfies the Grashoff's law. If this condition is not met, the mechanism will not function properly and may result in failure or instability.
Design implications of Grashoff's law. Grashoff's law has several practical applications in the design of machines. This law has significant implications in the design and analysis of machines, as it helps engineers determine the feasibility and stability of a mechanism. For example, it helps engineers determine the optimal placement of links in a mechanism to achieve the desired motion. It is particularly useful in the design of crank rocker mechanisms, which are commonly used in engines, automobiles, and machines. It also aids in the identification of potential design flaws and can assist in troubleshooting problems in a mechanism. When designing or analyzing a slider crank mechanism, carefully evaluating the Grashoff condition is crucial. It dictates the feasible range of connecting rod lengths that will permit full rotational motion without clashes. Respecting Grashoff's law ensures smooth, reliable functioning of the mechanism over extended operating cycles. This is because the shortest and longest links will intersect, preventing the mechanism from completing its intended motion. When the above-mentioned inequality is not met, the chain is classified as a non-Grashoff chain. In such a chain, none of the links can complete a full revolution relative to the other links. Four conditions are shown in the figure if the Grashoff's law condition are not met. Let us learn some inversions of the Grashoff chain law. We know that the process of fixing different links in a kinematic chain to obtain different mechanisms is known as inversion. In this Grashoff's law, inequality is not satisfied. No link will make complete revolution relative to another. Attention is called to the fact that nothing in Grashoff's law specifies the order in which the links are connected or which link of the four-bar chain is fixed. We are free, therefore, to fix any of the four links. When we do so, we create the four inversions of the four-bar linkage. All four inversions which fit Grashoff's law, and in each the link S makes a complete revolution relative to the other links. The different inversions are distinguished by the location of the link S relative to the fixed link. If the shortest link is adjacent to the fixed link, as shown in Figure A and Figure B, we obtain what is called a crank-rocker linkage. Link S is, of course, the crank because it is able to rotate continuously, and link P, which can only oscillate between limits, is the rocker. Next inversion, the drag link mechanism shown in the figure, also called the double crank linkage, is obtained by fixing the shortest link S as the frame. In this inversion, shown in the figure, both links adjacent to S can rotate continuously, and both are properly described as cranks. The shorter link out of these two links is generally used as the input link or driver. Although this is a very common mechanism, you will find it an interesting challenge to devise a practical working model that can operate through the full cycle. By fixing the link opposite to S, we obtain the fourth inversion, the double rocker mechanism of figured. Note that although link S is able to make a complete revolution, neither link adjacent to the frame can do so. Both must oscillate between limits and are therefore rockers.